Hello everyone. Good afternoon. Dear authors and invited guests, welcome to the technical session 9C. Myself, Vidhi Rangdale, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Congress on Information and Communication Technology, that is ICICT 2026, London, UK. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held day before yesterday in London, UK, and the virtual event is being held through Zoom from 25th to 27th February 2026. I hope you will enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for the presentation and 3 minutes for question and answers. On 10 minutes, I will raise a gentle reminder. There is another request to all the participants that you all stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in chat box. Just before we start the session, I would like to introduce all to the session chair. We have with us Dr. Deepak Mane. Dr. Deepak Mane is a professor and deputy director, IQAC, Vishwakarma University, Pune. With With 20 years of teaching experience, he has authored books on machine learning, fundamentals of programming languages, and principles of programming languages. His research primarily focuses on machine learning, deep learning, supervised clustering, and pattern classification. Welcome to the session, sir. Would you like to address the participants?
Yeah, thank you, ma'am, for a nice introduction. And yes, eagerly waiting for the presentation. Thank you.
Yes, sir. We will now move on to the first presenter. We now invite Talifani Calvin Shipota to present his paper titled Comparative Study of YOLO V8, YOLO V12, and Faster RCNN for Vehicle Detection under Adverse Weather Conditions.
Good, good day, or good afternoon, everyone.
Good afternoon.
Can you see my screen?
Yes, we can see your screen.
Okay, thank you. Good day. My name is Tarifani Calvin Chipota from South Africa, master's student. This will be my first time presentation in a conference. Please bear with me. I will be presenting our comparison study evaluating YOLO Vision 8 through Vision 12 against the first RCNN for vehicle detection under advanced weather condition. Reliable object detection plays a fundamental role in autonomous vehicle intelligence transport system and smart surveillance in environment. However, most object detection models are deployed and benchmarked under clear weather conditions. Sorry for that. In real world deployment, system must be operating under fog and reduced visibility. This study investigate which detection architecture maintain the best balance between accuracy and real-time performance when visibility is degraded. Okay, firstly, we'll go into our problem statement. Advanced weather conditions significantly affect image quality in fog environment. Light scatter reduction, cast, and blur object boundaries. In low light condition, signal noise ratio decreases, making feature extraction unstable. This degradation directly impact convolutional features map, which detect model rely on for classification and localization. Small objects such as motorcycle and people, sometimes it becomes difficult to detect those small objects. Small objects in safety critical systems such as autonomous driving. Even minor detection failure can have serious consequences. Therefore, robustness under degraded visibility is not optional. It is very essential. So our research objective, the primary goal of this research was structured benchmarking, specifically first to compare model YOLO architecture from Vision 8 through Vision 12 against the widely used fast RNN. And then secondly, to evaluate the detection robustness under fog and low light degradation. In the third, to measure not only detection accuracy, but also enforce latency. And finally, to determine which model provide the most balance for real-time deployment in advanced weather conditions. This is not simply about accuracy, and it is about deployability of the system. Okay, I will move to something very much crucial or important when we are doing our training, which is our experimental setup on how we set up and the data set we used when we are doing our training for this model. To ensure fairness and scientific rigor, all models were trained under identical conditions. We used the commonly used foggy space data set, which simulate a variety of fog density. All images were resized to 640 by 640 pixels, and each model was trained for 100 epoch using identical parameters. Hardware and GPU configuration were kept constant across the experiment. By controlling this variable, we eliminated experimental bias and ensured that the performance differences were due to architectural design, not training essentials. So just to make sure, and we also looked into our precision recall, F1 score, mean average precision at 0.5, and latency. So now I want us to go to look into our architecture. Understanding architectural difference is a key to interpret the result. YOLO model operate at a single stage detectors. They directly predict bounding box and class probability in an field forward pass. This end-to-end optimization reduce intermediate processes and computational redundancy. So first, uh, as for fast RCNN, on the other hand, it uses two-stage detection. The first stage is a reason proposal network generative candidate object region, and then these proposals are refined and classified in a second stage. While this design can be powerful in clear condition, it is increases computational cost and introduce dependency on high quality features map. Under fog, when feature map and degrade region proposal may already be inaccurate and error proposed to be in a second stage. These structural differences play a crucial role in performance under advanced weather condition. So now I want us to look into the accuracy comparison of this model that we trained. We trained YOLO 8, 9, 10, 11, and fast RCNN. And then if you look into the mean average precision at 0.5 for YOLO 8, we got approximately 0.61. For YOLO Vision 9, we got also got approximately around 0.69. And you go to 10, you look at 0.60, 11, and 12 as well. But for fast RCNN, we got, if you look into mean average precision, we got approximately 40%. When you look into the precision for YOLO Vision 8, we got 80%. And then for YOLO Vision 9, we got around 0.79. For Vision 10, we got 0.75. And then for Vision 11, we got approximately 0.78 as well as compared to Vision 9. This was training under fog and low light, just to remind people. And first RCNN, which the precision was around 0.49. And this training was not done once, it was tried to be done two or three times, just to make sure, to check if maybe in the previous training we didn't make, there was no any error, just to be sure. So now looking at this accurate table, all YOLO model achieved the mean average precision value approximately between 0.6 to 0.61, and the precision values ranging from 0.75 to 0.8. Importantly, performance remained resistantly stable across YOLO variation. In contrast, fast RNN demonstrated significantly degradation on this under dense fog condition and low light. So the key observation here is not just numerical differences, it's stability. YOLO model maintained consistency detection performance even when visibility was reduced. This suggests that the single stage detection pipeline may be more robust for future degradation. So now I want us to go and look into something also, interference time, which inference time, sorry. So now if you look into our YOLO Vision 10, it has a latency time of 15.9 millisecond, and YOLO Vision 8 has 16.8 millisecond, and YOLO Vision 11, sorry, has 17.1, and then YOLO Vision 12 have 20.0 millisecond, and YOLO Vision 9 have 28.0 millisecond. But if we look into the fast RCNN, in my case, the latency was around 85.1. At first, I trained this, and I also retrained again just to confirm, and I still continue to get the approximately the same value. Now, when we examine this inference time, YOLO Vision 10 achieved approximately 15.9 millisecond per image. Other YOLO variant range between, if you can choose, so there is between 18 and 16 and 28 millisecond. But however, first RCNN required approximately 85 millisecond, as I said, per image. This is more than 5 times slower. In real time, system operate at about 30 frames per second. Inference speed is very much crucial. A model request 85 millisecond per frame cannot sustain real time processing without hardware acceleration. So therefore, latency becomes a diversified factor in deploying feasibility. This is where YOLO Vision 10 demonstrates a clear practical advantage. So now I want to move to the speed accuracy trade-off. Although YOLO Vision 8 and 9 achieve slightly higher precision values, as we have seen, YOLO Vision 10 provided the most balanced trade-off. It maintained competitiveness in the mean average precision while significantly reduced latency. In safety critical application, achieving near optimal accuracy with sustaining lower interference time often perform on marginally higher accuracy with higher computational cost. So therefore, YOLO Vision 10 represent the optimal engineering compromises. So in this case, while we were training this, we also had other failure cases at which we would like to continue working to enhance on them so that we can
I
continue to
apologize
have.
for interrupting, but your 10 minutes are up. I request you to kindly proceed to the concluding part of the presentations as you have only 2 minutes remaining.
Okay, okay, thank you.
Thank you.
Okay.
So,
If I conclude in this research, if I conclude, the single stage yellow detection outperformed the two-stage fast RCNN under advanced weather condition. So yellow vision 10 provide the best balance between the computational efficiency and detection robustness with stable accuracy and over 5 times speed advantage. It is the most sustainable candidate for real time deployment in foggy and low light environment. So I believe in future, for future work, I'll try to explore gen-based image enhancement and transformation-based detection framework to further improve the robustness. Thank you very much for your attention, and I'm looking forward for your question. Thank you.
Okay, sir. When you compare different models like as yellow 8 to 12, you are saying V10 model is giving the better performance. So why it is stable?
Come again?
Hello, am I audible?
I Yeah, I can hear you, Doc.
Yeah, why V10 is stable?
V10 when I trained it, uh, I believe it was stable because of the mean average precision that I got. That's why I concluded that it feel like it's the one that is more stable.
Okay, and what are the challenges you face at the time of implementation?
The challenges that I found for the implementation, mostly it was on the machine because the machine that I was using, the GPU was very slow when I tried to implement it, which really affected my result in some cases.
Okay, okay, thank you.
Thank you.
we will now invite our next presenter. We now invite Sahil Datrange to present his paper titled EcoChain AI-powered verification system with blockchain security.
Good afternoon, everyone. So let's start with the presentation.
Good afternoon.
Is the screen visible?
Yes, we can see your screen.
Yes. Okay, so our project is EcoChain, AI-powered verification system with blockchain security. Our problem statement is in India, the farmers do not have knowledge about the income that they can earn via carbon credits. They can share their carbon credits and make some money out of it. And also, companies do not show their transparencies to the world according to carbon credits. So our project is there. So our project is a single marketplace where farmers and also companies could share their carbon credit systems and also buy carbon credits from those. And a second is that the companies could verify their carbon credits. Let's say I have a company, I want to buy 10,000 credits, but is those 10,000 credits really required for me? What is the real amount of credits requirement? So that also we have done. So this is the literature review. This is a base paper. We have totally gone through 30 papers, out of which 20 were based on such systems and 25 were based on the auto encoders model, and the 5 were based on the uh, isolation forest model. Okay, so the objectives. So to design a single marketplace where a company can buy carbon credit tokens, and also they could verify their carbon credits as well. To deploy, and also second objective is that to deploy all the transactions on blockchain, so to make sure these transactions are transparent and they are bulletproof. And also we have developed a full stack application where traders, verifiers, and also stakeholders could view this. We also have maintained a carbon credit registry so that all data and transactions are being noted. Okay, so this is a system architecture. So there are majorly four algorithms. First is the validation of the carbon credit. The second is minting of the carbon credit. Third is buyer and seller matching, and the fourth is the retirement process. So let's go through first one by one. So let's say I'm a farmer, or I'm a buyer. So I'm minting my carbon credits on the system. So what would I do? First, I will mint my carbon credit on the blockchain, and then they will be available on the blockchain. Now, when a company will purchase those carbon credit tokens, then a matching algorithm works over here. So it will match the user ID and then the seller ID, and will transfer the tokens. And also minting algorithm works at the first to tokenize these credits. Second, and also the most and important part is retirement and the burning of the carbon credit tokens. As you know, currently is very expensive. We can't just use blockchain technology for each and every purposes. So we have given particular time for each and every carbon credit token of 2 years. After that, they would be retired and burned from the system. The methodology. So first is input collection. That is a carbon credit token is collected from the verified farmers. Then they upload it, and then a verification report is generated. Then we tokenize those. We have used Polygon testnet for this. Polygon is basically a two-layer wrapper of Ethereum. We were planning to use Celo as well for blockchain technology, but Celo does not have that much security as compared to blockchain, and Celo is not as fast. We want something that is more fast, so we opted for Polygon testnet to deploy a blockchain. Third is storage in the carbon credit registry. We have to create a carbon credit registry to monitor each and every token. So it is not like we are measuring the amount. We have just storing the hash ID over there to verify for further if any misuse happens. Then the smart contract creation and marketplace integration, where we have developed a single marketplace where seller could just upload their CCTs, that is carbon credit tokens, and companies could buy those and then transfer it and then audit. This is the data verification process. So for this, we have taken data from real-time data from the CDP, that is Carbon Disclosure Project. Under it, we got data of companies and their level 1 and level 2, scope 1 and scope 2 emissions of carbons. So according to it, we will train a model. So for this we have created a hybrid model of isolation forest and autoencoders. Okay, so let us look to the results. So first, the isolation forest. So the isolation forest gives an accuracy of 90.18%. The autoencoders give an accuracy of 85%. But a merge model, where we use an hybrid model of these two models, and if one fails, that our model depends on the other. So basically, our merge model accuracy is 92.47%. So over here, you can see that the carbon credits have been transferred from one account to other. This is the contract generation, deployment, and as well as the result of carbon credit token shifted. Over here, you can see on the top right corner, you can see the data cleaning process. Below that, there is company dashboard, where a company could view the available credits, the price of it, and they could buy them. This is a verification report. It gives a report of how much percent of the data is accurate or not. Again, this is the vendor dashboard or the farmer dashboard, where he could add the carbon credit and mint that credit on the blockchain. And over here also, companies could view their profile portfolio, that from which farmer they have bought, how much tokens, and how much total tokens they have available. And lastly, after the token is generated, right, so there should be some sort of proof, right? So this is the certificate that we will issue. So over here you will get the invoice number, the date, the buyer name, the seller name, and also the how much amount of credits were purchased, and also what was the total cost, and also the hash ID with it. So basically this would be mailed to your official email. Conclusion. So, according to our project, it empowers farmers to have another source of income, that is CCT, and also monitor this carbon credits and make sure that companies do not misuse it. Thank you.
Okay, so how you compare your result with existing approaches.
Yes. So if you see the existing approaches, let's say for blockchain as well. So for blockchain, they are using Ethereum, which is currently outdated, and also they are not referring to the burning and the retirement process. That is the complete block cycle, complete life cycle of a carbon credit token. Because it is very important when we deploy something, we have to remove that carbon credit from the blockchain as well. Some papers do not have done that, so that is the plus point of it. And second is the hybrid model that we have made for verification, data verification. So we have made a hybrid model of autoencoders and isolation forest. So that results would be a hybrid of both. So if one model fails, the other catches up and makes sure that anomaly is properly detected.
Okay, and what is the impact on result?
Yes, sir. So the result is accuracy is increased. So basically, from recent studies, we got to know that accuracy is between 8.87% to 91.5%. But our current merged model gives an accuracy of 92.47%, which is increased.
Okay, good, nice. Thank you.
Thank you, sir.
We would now ask to present to the next presenter. We invite Sylvester Kaczmarek to present his paper titled Hardware in the Loop Validation Protocol for Event-Driven Neuromorphic Safety Monitors. It seems like he is not in the meeting right now. We will move on to the next presentation. We now invite Hikma Ramadhani to present her paper titled Mapping the Intellectual Landscape of Public Opinion Studies in the Digital Age, a Bibliometric Perspective.
Okay, thank you for very much for opportunity. I will share my presentation. Okay, good afternoon, everyone. My name is Ramadhani from Hasanuddin University, Indonesia. Today, I will present our research entitled Mapping the Intellectual Landscape of Public Opinion Studies in the Digital Age, a Bibliometric Perspective. This study aims to systematically map how public opinion research has evolved in the context of digital transformation, especially under the influence of social media and algorithmic communication. Public opinion plays a central role in modern democracy. It connects citizens with policymakers and shapes government's decisions. However, the digital transformation has fundamentally changed the landscape of political communication, social media platform, personalization algorithm, and computational data system now influence how options are formed, circulate, and amplified. Despite the growing volume of research, there is still a lack of systematic mapping of the intellectual structure
I'm
and
sorry to
thematic.
interrupt, ma'am. I'm really sorry, but we are not able to see your presentation. We are able to see the PowerPoint application only.
Oh, sorry.
Yes, ma'am. Sorry for the interruption.
My slide blank or not?
Yes, your presentation is visible now. Thank you. We can see your presentation now.
Okay, I continue. And despite the growing volume of research, there is still a lack of systematic mapping of the intellectual structure and thematic evolution of public opinion studies in the digital era. Therefore, this research address that gap by using a bibliometric approach to identify trends, dominant themes, global distribution, and research collaboration patterns. And next, methodology. In this study, we employed a bibliometric analysis method using data extracted from international indexed publications. We analyzed publication growth, geographic distribution, keyword co-occurrence, and thematic clustering. Bibliometric analysis allows us to visualize the intellectual structure of a research field and identify emerging patterns and conceptual relationships. Growth in public opinion research. Our findings show significant growth in public opinion research. Between 2019 and 2024, publication increased by 56.8%. The number of documents rose steadily from 1,668 in 2019 to 2,223 in 2022 and peaked sharply in 2024 with 2,616 articles. This indicates increasing scholarly attention toward public opinion in the context of digitalization and political polarization. This is global distribution. The global distribution analysis shows that research in this field is geographically concentrated. The top 10 countries produced 9,020 publications. The United States dominates with 38.6% of total output, followed by the United Kingdom and China. This dominance suggests that Western and developed countries still act as intellectual center in public opinion research. And next, major thematic clusters. Our analysis identifies four dominant and interrelated thematic cluster. For the first, digital dynamics, and second, governance and trust, and third, democratic legitimacy, and four is polarization. The clusters show that research has shifted from traditional opinion policy models to algorithm-driven digital complexity. This is visualization result. The keyword network visualization revealed that public opinion remains the central node of gravity. Key channels such as social media, climate change, and democracy serve as bridges connecting thematic areas. Emerging keywords like environmental impact and adaptation indicate growing interest in sustainability-related discourse. Methodologically, computational tools such as sentiment analysis and large-scale surveys are increasingly dominant, showing a shift toward data-driven approaches. And next discussion, the digital reality. In the discussion, we highlight three important digital realities. First, echo chambers, algorithm reinforce existing beliefs, leading to fragmented opinion clusters. And second, biased projection. Politicians often misinterpret public opinion due to selective exposure or polling bias. And third, academic echo chambers. Research collaboration tend to concentrate within specific networks, potentially limiting intellectual diversity. This suggests that digital transformation not only reshapes public discourse, but also academic production itself. And conclusion and future research gaps. In conclusion, the field of public opinion studies has evolved significantly. It has shifted from linear policy response models to complex analysis of algorithmic influence and polarization. However, several research gaps remain. First, the psychological impact of algorithm on political behavior. And second, strategies for public communication in fragmented digital space. and third, the effectiveness of traditional political representation in highly digitized society. These areas present promising direction for future interdisciplinary research. And the last reference, our study builds upon recent contribution in political communication, public opinion theory, and digital governance as listed here. Okay.
Okay, so ma'am, what is your contribution?
Sorry?
What is your contribution?
My contribution.
Yeah.
For this, I'm just only researcher to this paper, and my contribution.
Okay. 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 So this is like as a survey. Is it correct?
Sorry?
So is it like as a survey? Is it correct? You are just study the existing approaches. Okay. Okay. No issue, ma'am. Okay. Thank you. No issue.
We will now move on to the next presentation. I now invite Kartika Suryabhani to present her paper titled Parasocial Relationships on Social Media, Research Trends, Influential Works, and Future Research Pathways. It seems like she is not in the meet. We will move on to the next presentation. We now invite Sylvester Kaczmarek to present his paper titled Quantifying Threat Synergy in Multi-Domain Stress Testing for Autonomous Systems. We have any of the two authors mentioned in the meeting? Kartika and Sylvester. As they are not available in the meeting, we will now move on to the closing part of the session. I sincerely thank our authors for their excellent presentations and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for the support during this 11th version and all the previous 10 versions of the conference. We will be happy to have you in the 12th version in 2027. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live 7 to 8 months. Kindly cooperated with the team of ICICT 2026. I would now like to present the certificate that will be shared as a token to the session chair.
Thank you, ma'am. Thank
We
you.
thank you for chairing this session, sir. A token of appreciation to the chair on behalf of Team ICICT 2026 and Global Knowledge Research Foundation and partners. Thank you for a very valuable presence, everyone. I would now like everyone to switch on their cameras to capture this meeting end. Thank you, everyone. I hope you have a great day ahead. Stay safe. Thank you.
Thank you.